The theory of diffraction grating. We have seen in the previous discussion that when the number of slits n approaches infinity, only the principal maxima remains as very bright and the lines become narrow. And this is the principle by which a diffraction grating has been constructed. A grating is an arrangement that consists of a large number of equidistant slits as you see in this figure. The grooves in the grating are cut at regular intervals d. The places where the grooves appear will be opaque and the adjacent spaces will be transparent. So a grating is basically an arrangement of transparent and opaque spaces. Let us assume that the width of the transparent space is A and the width of the opaque space is B. In that case, D will be equal to A plus B. And the diffraction pattern that is generated by a grating is known as a diffraction spectrum. And a good quality grating requires a large number of slits, typically about 1500 per inch. This figure shows the diffraction pattern that is generated by a diffraction grating. We have a central maxima and the different orders of the spectrum will be placed on either side of the central maxima. Since the exact positions of the principal maxima in the diffraction pattern depend on the wavelength, the principal maxima corresponding to different spectral lines that are associated with the source will correspond to different angles of diffraction as you see in this figure. Let's discuss how these diffraction gratings are made. Diffraction gratings are typically made on an optically transparent sheet of material. The grooves are ruled with a diamond point. The grooves act as opaque spaces, and for good quality gratings, the lines should be as equally spaced as possible. Commercial gratings are typically made by taking the cast of an actual grating on a transparent film, like that of cellulose acetate. An appropriate strength solution of cellulose acetate is poured on the ruled surface and allowed to dry to form a strong, thin film which can be detached from the parent grating. These impressions of a grating are preserved by mounting the film between two glass plates. Nowadays, gratings are made using holographic techniques. Here, one records the interference pattern between two plane or spherical waves in a media. In contrast to ruled gratings, holographic gratings have a much larger number of lines per centimeter. In a diffraction grating, the positions of the principal maxima are given by d sine theta equal to m lambda, where m is equal to 0, 1, 2, 3, etc. This equation is known as the grating equation and can be used to study the dependence of the angle of diffraction theta on the wavelength. In the figure on the right, you can see the different orders of the spectrum corresponding to m equal to 1, 2, 3, etc. The 0th order principal maximum occurs at theta equal to 0 irrespective of the wavelength. Thus, if we were using a polychromatic source, then the central maximum will be the same color as the source itself. That is, if you use a white light, the central maxima will be white in color. For m not equal to 0, the angles of diffraction are different for different wavelengths. Therefore, various spectral components appear on either side of the central maxima at different positions. The intensity of the spectra will be maximum for the 0th order spectrum, where no dispersion occurs, and the intensity falls off as m increases. We'll now discuss about some deductions from the grating equation. The grating equation is given by d sine theta equal to m lambda, where m equal to 0, 1, 2, etc. When we differentiate this equation once, we'll get delta theta over delta lambda as equal to m over d cos theta. Let's now analyze this equation. If we assume theta to be very small, that is cos theta approximately equal to 1, we can see that the angle delta theta is directly proportional to the order of the spectrum for a given delta lambda. That means that for a given m, delta theta by delta lambda is a constant. And such a spectrum is known as a normal spectrum. In this case, the difference in angle for two spectral lines is directly proportional to the difference in wavelengths. However, for large theta, the dispersion is greater at the red end of the spectrum. The second deduction. We see that delta theta is inversely proportional to d. Therefore, smaller the grating element, larger will be the angular dispersion. Let's try to solve this problem. A parallel beam of light of wavelength 5460 angstrom is incident at an angle of 30 degree on a plane transmission grating which has 6000 lines per centimeter. Find the highest order spectrum that can be observed. In this case, theta is given to be 30 degree and the wavelength lambda as equal to 5460 angstrom, which is equal to 5460 times 10 raised to minus 10 meter. N is the number of lines per centimeter, and that is 6000 lines per centimeter. And the grating element D will be equal to 1 over n, and this is 1 over 6 times 10 raised to 3 centimeters, and this is equal to 1 over 6 times 10 raised to 5 meter. The grating equation in this case can be written as d sine theta m plus sine I, and this is equal to m lambda. But in this case, theta m is equal to I. Therefore, d times 2 sine I is equal to m lambda, and this gives us m as equal to d times 2 times sine I divided by lambda, and this is 1 over 6 times 10 raised to 5 times 2 times sine 30 divided by 5460 times 10 raised to minus 10, and this is equal to 3.05 or 3. So this is the order of the highest spectrum that is observed. Exercise 8. Calculate the possible order of spectra with a plane transmission grating having 18,000 lines per inch when light of wavelength 4500 angstrom is used. The grating equation is d sine theta equal to m lambda, which gives m as equal to d sine theta over lambda. The highest order occurs when theta equal to 1. Therefore, m equal to d over lambda, and this is equal to 1 over 7.09 10 raised to 5 lines per centimeter multiplied by 4500 power 10 raised to minus 10 meter. This will give us m equal to 3. Exercise 9. Light, which is a mixture of two wavelengths 5000 angstrom and 5200 angstrom, is incident normally on a plane transmission grating having 10,000 lines per centimeter. A lens of focal length 150 centimeter is used to observe the spectrum on the screen. Calculate the separation in centimeter of the two lines in the first order spectrum. We are given that d equal to 10 raised to minus 4 centimeter. There are two wavelengths. Lambda 1 is equal to 5000 angstrom, and that is 5 to the power 10 raised to minus 5 centimeters. And lambda 2 is equal to 5200 angstrom, and this is 5.2 times 10 raised to minus 5 centimeters. And the order m is equal to 1. We have sine theta 1 as equal to m lambda 1 over d, and this is equal to 1 times 5 times 10 raised to minus 5 over 10 power minus 4. This will give theta 1 as equal to sine inverse 0.5, and this is equal to 30 degree. And sine theta 2 is m lambda 2 over d, and this is equal to 1 times 5.2 times 10 raised to minus 5 over 10 raised to minus 4. This results in theta 2 as equal to sine inverse 0.52, and this is equal to 31.3 degree. To proceed further, consider this schematic. Let us assume that the wavelength lambda 1 occurs at B and lambda 2 occurs at A. The diffraction angle for lambda 1 is theta 1, and that for lambda 2 is theta 2. Lambda 1 is at a distance x1 from the center of the screen, and lambda 2 is at a distance x2 from the center of the screen. And we want to find out the separation in centimeters of these two lines in the first order spectrum. That is, we have to find out x2 minus x1. From this figure, we can write tan theta 1 as equal to x1 over f, and tan theta 2 as equal to x2 over f. And this gives us x2 minus x1 as equal to f times tan theta 2 minus tan theta 1. And this is 150 times 0.0687 minus 0.5774, which is 4.7 centimeters. That is, the two spectral lines in the first order spectrum are separated by a distance of 4.7 centimeters. Exercise 10. Consider a diffraction grating with 15,000 lines per inch. Show that if we use a white light source, the second and third order spectra overlap. What will be the angular separation of the D1 and D2 lines of sodium in the second order spectra? Let's try to do the first part. The grating element is D equal to 1 over 15,000 inch. And this is equal to 2.54 over 15,000 in centimeters. So this is equal to 1.69 power 10 raised to minus 4 centimeter. Let us now assume theta mv and theta mr as the angles of diffraction for the mth order spectrum corresponding to the violet and red colors respectively. Thus, for the violet line, we have theta 2v equal to sine inverse m lambda divided by d, and this is sine inverse 2 multiplied by 4 power 10 raised to minus 5 over 1.69 times 10 raised to minus 4. And this is approximately equal to sine inverse 0.473, and this is equal to 28.2 degrees. For the red line, we have theta 2r equal to sine inverse m lambda divided by d, and this is sine inverse 2 times the wavelength of red line divided by 1.69 10 raised to minus 4, and this is approximately equal to sine inverse 0.828, which is 55.9 degrees. And theta 3v is sine inverse 3 times 4 times 10 raised to minus 5 over 1.69 power 10 raised to minus 4, and this is approximately equal to sine inverse 0.710, and this is equal to 45.23 degrees. We see that sine theta 2r is greater than sine theta v. That is, the second and third order spectra will overlap. Further, since theta 3r is greater than 1, the third order spectrum for the red color will not be obtained. Now, the part B of the problem. We have d sine theta as equal to m lambda, and for small delta lambda, we can write d cos theta delta theta as equal to m times delta lambda. This will give us delta theta as equal to m delta lambda over d cos theta. To devise an expression for cos theta, let us consider the trigonometric equation cos square theta plus sin square theta as equal to 1. From here, we'll get cos square theta as equal to 1 minus sin square theta. And this is nothing but 1 minus m lambda over d the whole square. Hence we write this equation as m delta lambda over d times 1 minus m lambda over d the whole square to the power 1 by 2. Therefore, delta theta, which is m delta lambda over d, then 1 minus m lambda over d the whole square to the power 1 by 2, and this is equal to 2 times 6 power 10 raised to minus 8 over 1.69 times 10 raised to minus 4, then square root of 1 minus 2 power 6 to the power of 10 raised to minus 5 over 1.69 to the power of minus 4 the whole square. And this is equal to 0.001 radians, which is approximately equal to 3.47 minutes. The resolving power of a diffraction grating. Resolving power of a grating refers to the power of distinguishing two nearby spectral lines, and it is given by the relation R equal to lambda over delta lambda. Here, delta lambda refers to the separation of two wavelengths which the grating can resolve, and smaller the value of delta lambda, larger will be the resolving power. Now, how do we define the limit of resolution of two nearby spectral lines? It is given by the Rayleigh criterion. Let us assume that we have two closely spaced wavelengths, lambda and lambda plus delta lambda. And this one is lambda. In this figure, the principal maxima of lambda plus delta lambda is shown to fall on the first minimum of wavelength lambda. If that is the case, according to Rayleigh criterion, these two spectral lines will be resolved. Now consider this figure. In this figure, Mn represents a screen on which we have diffraction patterns of lambda and lambda plus d lambda is produced. The principal maxima of lambda occurs at P1 and that of lambda plus d lambda occurs at P2. And the maxima of lambda plus d lambda falls at the first minima of lambda. Now, the direction of the mth primary maximum for a wavelength lambda can be written as d sin theta equal to m lambda. Let us call this as equation number 1. The direction of the mth primary maximum for a wavelength lambda plus delta lambda is given by d sin theta plus d theta equal to m lambda plus d lambda. Let it be equation number 2. And these two spectral lines will appear just resolved if the angle of diffraction theta plus delta theta also corresponds to the direction of the first secondary minimum after the primary maximum at P1. So this is possible if the extra path difference introduced is lambda over n, where n is the total number of lines on the grating surface. That is, for the minima of lambda, we can write d sine theta plus d theta equal to m lambda plus the path difference lambda over n. Let this be equation number 3. So this is the equation for the minima, and equation 2 is for the principal maxima at P2. Since these two fall at the same position, we can equate equation 2 and 3. That is, m lambda plus d lambda equal to m lambda plus lambda over n. And this gives us m d lambda equal to lambda over n, or lambda over d lambda equal to m times n. And this gives the expression for the resolving power of a diffraction grating. Thus we see that the resolving power of a grating is independent of the grating constant d. The resolving power is directly proportional to the order of the spectrum and the total number of lines on the grating surface. For a given grating, the distance between the spectral lines is double in the second order spectrum than that in the first order spectrum. Another important parameter with respect to a diffraction grating is its dispersive power. The dispersive power of a grating is defined to be d theta over d lambda, and this is equal to m over d cos theta. And this can be written as m n dash over cos theta, where n dash is 1 over d. Here m is the order of the spectrum, n is the total number of lines on the grating surface, n dash is the number of lines per centimeter on the grating surface, theta is the direction of the mth principal maximum corresponding to a wavelength lambda. This is a comparison of the dispersive power and the resolving power of a grating. The dispersive power is defined to be d theta over d lambda, and that is m over d cos theta, which is again equal to m n dash cos theta. Whereas the resolving power is lambda over d lambda equal to m times n. N dash is the number of lines per centimeter on the grating surface, and n is the total number of lines on the grating surface. So it is clear that the dispersive power increases with increase in the number of lines per centimeter, whereas the resolving power increases with increase in the total number of lines on the grating surface, that is, the total width of the grating surface. And high dispersive power refers to wide separation of the spectral lines. and high resolving power refers to the ability of the instrument to show nearby spectral lines as separate ones. Exercise 11. Light is incident normally on a grating of total ruled width 5 times 10 power minus 3 meter with 2500 lines in all. Calculate the angular separation of the two sodium lines in the first order spectrum. Can they be seen distinctively? In the problem, it is given that n equal to 2500. That is the total ruled width of the grating. And b as equal to 5 times 10 raised to minus 3 meter. The order m is equal to 1 and lambda 1 for sodium line is 5890 power 10 raised to minus 10 meter, and lambda 2 is equal to 5896 times 10 raised to minus 10 meter. And we have the number of lines per meter. This is 2500 divided by 5 times 10 raised to minus 3, and this is equal to 5 times 10 raised to 5. And therefore, d is 1 over 5 times 10 raised to 5, and this is equal to 2 power 10 raised to minus 6 meter. For the first order, m equal to 1 and sine theta 1 is equal to m lambda 1 over d, and this is equal to lambda 1 over d. This is 5890 times 10 raised to minus 10 centimeter over 2 power 10 raised to minus 6 centimeter, and this is equal to 0.2945. And sine theta 2 is equal to m lambda 2 over d, that is 5896 times 10 raised to minus 10 centimeter divided by 2 power 10 raised to minus 6 centimeter, and this is equal to 0.2948, and this is 17 degree 9 minutes. This will be 17 degree 8 minutes. Now the resolving power of the grating is lambda over d lambda, and this is equal to 5890 times 10 raised to minus 10 centimeter divided by 6 power 10 raised to minus 10 centimeter, and this is equal to 982. As the total number of lines on the grating is 2500, which is more than 982, the lines will be seen distinctly.